So let me introduce our speaker. We have a great pleasure to have him as our speaker for our SciML seminar. Simo Sarkka, he is well known in the areas of Bayesian filtering, stochastic ODEs. He has written a couple of books. His book on Bayesian filtering is highly cited, is widely read, and he also more recently has a book on stochastic differential equations, which is also having a good impact. So Simo received his Master of Science in Engineering Physics and Mathematics and Doctor of Science in Electrical and Communications Engineering from Helsinki University of Technology in Finland. And currently he is an associate professor at Aalto University and adjunct professor at Tampere University and LUT University. He has many accolades, and he, has authored or co-authored more than 150 peer-reviewed scientific articles, and the books that I already mentioned. There is even translated in Chinese. And he's a senior member of IEEE and is serving as senior area editor of IEEE Sigma Processing Letters. So, like I said, it's a great pleasure, and especially because Simo is also a close collaborator. We are collaborating on a joint project, NSF Academy of Finland, and so we are really happy to have him. Thank you, Simo. So the floor is yours. Thank you.
Okay, so thank you for the introduction indeed. And the topic of my talk is probabilistic solvers for ODEs and PDEs. So I will start by, introducing, so what is the problem that we are solving and what's the basic idea. And then I will, explain how to do probabilistic ODE solving and how it can be seen as Gaussian process regression. Then I will discuss about reformulation of Gaussian processes in terms of Bayesian filters and smoothers, and then how to reformulate the ODE solving, probabilistic ODE solving as Bayesian filtering and smoothing. And then there's a small discussion about extension to partial differential equations. I think there would be more to discuss also in the future, but there's a brief discussion on that. And then finally is the conclusion. So let's start with seeing what is the problem that we are solving, or what's the basic idea. So the problem formulation is that we have an ODE, meaning ordinary differential equation, where this x is a vector of state variables, and then f is some nonlinear function of the state variables, and then there's everything is, or the solution is a function of t, so t is the independent variable. So we somehow want to compute the solution, which means that we want to solve the function like this with somehow. So this blue is the actual solution. And in particular, like I'm going to discuss initial value problem. So we have some initial x not given at time 0. And we are looking at the approximate solving of ODEs, so that the approximate solution can be seen as x hat, which is an approximation in the sense that it's somehow approximately equal to the actual solution at certain finite number of points, x0, x1 until xn. And so, for example, these orange dots on the right, or orange stars, could be the t1, t2, or these discretization points. And the idea is that this f is only evaluated at these grid points or some nearby points. Well, typically it's, so we only allow for evaluations at, well, maybe those points and then maybe some nearby points. For example, in Runge-Kutta methods, you actually allow for more than evaluation at those points. But we can define that this X hat is called a numerical solver of an ODE if we use a mathematical definition. And we want to find that kind of approximate solution to the ODE. Classically, how we proceed is that, well, okay, so we have some kind of approximation to the ODE, which is the X hat. And then typically how we, well, quantify the error, which we also try to minimize in the end, is the worst case error. So on the right, well, these are some kind of error bars, and we want to bound the maximum possible error that we can have. And that kind of error can be quantified by using Taylor's theorem. And the difference in probabilistic solvers is that this error is not quantified by the worst case error, but instead we try to compute some kind of probabilistic bounds for the error. So the lower figure here is trying to like illustrate that, okay, so there's a distribution of possible solutions, and then we want to quantify the distribution of the error in these approximate solutions. These two things are not completely different things, because probabilistic solvers also deal, or they are in a sense equivalent to worst case bounds in terms of Sobolev norms. So if we assume that these functions belong to certain Sobolev space, we have a like a worst case bound on the error in terms of those norms. But okay, so I'm not going to go into those details in this talk. But instead, we will try to derive these probabilistic error quantifications for the ODE solvers. And so actually first we need to replace the Taylor's approximation with something else to be able to do that. So the classical ODE solving can be seen as a form of polynomial fitting. For example, the Euler method, what it does is that it can be seen to form a piecewise linear approximation to the ODE solution. So that if we have a 1D case, then x of t can be Taylor expanded as a x of t naught plus the derivative of x at time t naught times t minus t naught plus higher order terms. But if you use linearization, so we just retain these first two terms, and then, well, this derivative is equal to f evaluated at x t naught. So this forms the basis of the Euler approximation. And then we can iterate this approximation to form an approximate solution to the ODE. Then, for example, Runge-Kutta methods, if we look at how they are derived, they are actually based on higher order polynomial expansions. So there the idea is that, okay, so in principle, we can form the Taylor series solution to an ODE by expanding these terms in as higher order time derivatives. Well, we could kind of evaluate these higher order derivatives also by differentiating f multiple times, but that is not how Runge-Kutta works. But how Runge-Kutta works is that we evaluate cleverly the function f at certain nearby points, so that those higher order or the errors cancel out in a certain way, and actually the interpretation is that this Runge-Kutta method forms a polynomial approximation of the solution by finding these coefficients by using multiple evaluations of the right hand side of the ODE in a clever way, I would say. But anyway, it's a polynomial fitting to the solution as well. But the nice thing is that because this is just a does the polynomial approximation, we can actually analyze the worst case error by using the Taylor's theorem, which is indeed the beauty of the classical ODE solving theory. But this is not probabilistic. This is just the worst case. Okay, so there's still illustration is that Euler somehow approximates the solution, roughly speaking, by using piecewise linear functions. That's not the whole truth, but anyway, roughly speaking. And then we could think about the higher order approximation, so that these are a bit curved and it's more approximate. So this is honestly speaking, this is not the actual Runge-Kvitte, but it's illustrating a polynomial fit. So it would correspond to actually second order method. But anyway, polynomial approximation is better than the linear approximation. So you need less, or you can use like a longer time steps to get equivalent approximation accuracy. But there exist a lot of other kinds of regressors than polynomial regression. So in particular, machine learning and statistics provide all kinds of approximation models. For example, we have neural networks, which are, well, flexible and they are used a lot in classification tasks. But in principle, you can also use them in regression tasks. And so they are very flexible and can be very accurate, but actually they are quite slow to train. So we couldn't just like train neural networks when solving an ODE. Because that's what happens. You fit the polynomial at each time step when you solve an ODE using polynomial approximations. And that wouldn't be feasible for neural networks. So instead, Gaussian processes, which also are used in machine learning a lot, turn out to be suitable because they are fast to fit data, and they also provide error bounds, and they happen to actually provide probabilistic error bounds. So that's actually why they are going to be used here. And indeed, what these probabilistic ODE solvers are, which I'm going to discuss. So the idea is to replace the polynomial approximation in the ODE solver by using a Gaussian process. So then we get better approximation and also on probabilistic error bounds for the solutions. So let's see then how we can actually do it. So first, let's recall what is Gaussian process regression. So we need to be careful with notation a bit, because typically in Gaussian process regression in the machine learning, you denote inputs by X and maybe outputs by Y or even T. So we have a quite orthogonal notation to our ODE solvers. So, but anyway, so we can consider Gaussian process as an unknown function from X to Y. Let's be careful with my X here. And so we want to predict the value of the function at certain test point X star based on some finite number of training samples, Xj, Yj, which we have observed from it. So we can think about like a series of dots, and then we don't know the function at 12 at 12. Okay, so you know, you can visualize the problem like that. And indeed, for the notation's sake, because we are actually dealing with functions of time, because we are solving ODEs with the independent variable being the time, it's convenient to replace X with T. So we're actually interested in functions G of T. So Y is equal to G of T. And we only get to know the functions G of T as via evaluation at finite number of points, well, finite number of T values or input values. And in classic regression, including polynomial regression and linear regression, we would postulate the parametric form of that G. So say that, okay, G of t is some kind of function of theta vector, for example, a linear combination of basis function and then multiplied by thetas. Basis functions could be the polynomials or something like that. And then we would estimate the parameters theta somehow, for example, by least squares or stochastic gradient descent or well, in multiple ways. But in a Gaussian process regression, we instead assume that G of t is a priori a sample from a Gaussian process with certain covariance function. So the typical covariance function which is used is this kind of Gaussian shaped cost function, covariance function, which is like a constant times then e power to minus the squared distance between the time points. So it tells that nearby points are more correlated than the points which are far from each other. So we can imagine that we would have this covariance function for the Gaussian processes for now. And so what the Gaussian process regression actually looks like. So it is pretty simple, provided that we fix the hyperparameters. So we can actually code it up with a couple of lines of code, which will be important because we need to be able to do that solution at each time step for the ODE solver, at least in the first version of the ODE solver, which we will develop. So let's denote this vector of observed points as y, capital Y, well, bolded Y, not capital. So it contains these observed points from y1 to yn. And then we have a test point y star, which is the value of G at t star. And t star is the test input position where we want to evaluate our value of the function. And then how we derive a Gaussian process regression is that the Gaussian assumption just implies is that the joint distribution of y and y star has to be Gaussian. And that covariance function actually gives the covariance between these points, so we can form the joint covariance matrix. And then, well, we typically assume that it's a priori zero mean. That can be relaxed, but anyway, let's assume zero mean for now. And here, indeed, these are just blocks from the covariance function evaluations at the known points, and then at the test point, and then like jointly at the test and observed points. And then, okay, so we know y, bolded y, but we don't know y star, but we can just compute the conditional distribution of y star given bold y, and that will be Gaussian. So it turns out that this value of G at t star is Gaussian random variable with certain mean and certain covariance, or certain variance in this case, because it was 1D. And so these equations can now used for interpolating value y at G evaluated at, which is G evaluated at t star. And that is indeed the Gaussian process regressor in the case of no noise. But we can also consider noisy measurements. So y is equal to G of t and plus some kind of noise, well, Gaussian noise. And then we want to evaluate somehow the value of the clean function at the test point. But almost the same derivation works. So we can still write down the joint distribution of y, which now also contains an additional component due to noise. But then jointly with G of t star, we can write down the covariance function. And then we can write down the conditional mean and conditional variance of the value of the test function at the test point, or value of the function at the test point. So these are very typical GP regression equations, which you actually see in practice. So these are scalar special cases, but actually quite simple generalization. You can also get multivariate versions of these. And so what Gaussian process regression looks like. So here we have this green is a Gaussian process without any conditioning on the observations. Maybe if you condition on the first observation, it's easier to see what happens. So this green is the 95% quantile, and this is the mean of the function here. So without any observations, we have just a zero mean and large variance. But then when we condition on one measurements, we get more certain prediction around that point. But then in other places, it's much more uncertain. But then we can condition on additional points. And the mean of the Gaussian process will follow this sinusoidal curve, which is run through quite well. And then also the uncertainty tells like how certain we are about the point at each place. Okay, but then it turns out that we can also measure derivatives instead of like having the plain values quite easily. So that if we actually have like this y dot, this is just a notation for noisy derivative measurements. So we measure derivative of g with respect to t plus noise. Then it turns out that we can actually redo the same derivation, and then if we know the covariance function of g, then it's quite easy to show that the covariance function of the derivative of g is just the derivative of the covariance function. So it turns out that just by differentiating that the covariance function, so recall that we know the covariance function, so it was just that e power to minus t prime. So we can actually compute these values. So that by using the derivative measurements, we can still recover the function at the test point, for example. Well, to be precise, we could also kind of estimate the derivative, but okay, so we can also use derivative measurements in Gaussian process regression quite easily, and even mix those with the ordinary measurements of the Gaussian process. So let's see how we can actually use these concepts to solve an ODE. So let's consider that we have this ODE in scalar case. So dx dt is equal to f of x, t, and t, and then we have some kind of initial conditions here. And now idea is that we form a GP regressor. So we denote it like this: g of t is a Gaussian process with zero mean, and then some given covariance function. So for example, this could be that e power to minus t prime. And then we want to approximate the solution g of t or x of t by g of t. And then how we do that is that, well, first we have this Gaussian process, that green one, which is not conditioned on anything, but then we condition that Gaussian process on these so that it solves this ODE at the finite grid. So we say that, okay, so the derivative of Gaussian process minus f evaluated at the Gaussian process needs to be zero, which tells that, okay, so this ODE is solved by the Gaussian process at this points t n. But now recall that we kind of can handle time derivatives of Gaussian processes, and then this second term here is just the nonlinear transformation of the Gaussian process. So it turns out that this defines a nonlinear likelihood that can be handled with nonlinear Gaussian process methods. So actually, precisely speaking, this is a constraint, but it can be handled actually in a similar way as you would handle nonlinear likelihoods. So that we can solve the problem was, so this is a Gaussian process, and then we have a nonlinear likelihood, and then we can run like a nonlinear optimizer to find the maximum likelihood Gaussian process, for example. And that is the probabilistic ODE solver, at least in principle. So that is how it was first actually implemented even. But there's a bit of challenge because solving these nonlinear Gaussian process regression problems at every step is a bit computationally heavy. So this is not very practical. So we need to do something else. And indeed, that's where this reformulation as Bayesian filtering and smoothing helps. So the motivation for doing that is that the computational complexity of Gaussian process regression is actually cubic in the number of measurements n. That's because if we take a look at the equations which we derived, so there's a, so this is actually n times n matrix, and then there's at least implicitly like it's an expression which contains n times n matrix inversion inside. Of course, we can also use things like Cholesky factorization to, we don't actually need to explicitly compute the inversion, but it turns out that the complexity is still O n to the power 3. And so we could try to use some tricks is that let's keep n small. So instead of having a whole grid in the Gaussian process regressor, we can somehow just say that n is 3. But the problem is that that loses information. So we want to actually do a full Gaussian process regressor on the whole ODE to use all the information and have the precise uncertainty quantification in our solver. There exist sparse and reduced rank and other related approximations that have been developed for this purpose. But here we will use another method, which is actually, so my group has been studying that quite a lot. So it's also possible to reduce GP regression to Kalman filtering and smoothing problem, which then has linear ON complexity, provided that the Gaussian process is only a function of time. And it happens to be over here. So that's very well suited for this purpose. So let's see how it can be done. So background is that there are multiple ways to represent the Gaussian process. So how it's done typically in machine learning is that you fix the covariance function. So it could be that like a squared exponentiated quadratic or squared exponential covariance function, which looks like an unnormalized Gaussian. But okay, so for example, if it would look like this, so covariance function is only one way to represent that. So provided that it's stationary, we can take the Fourier transform of the covariance function, which gives the spectral density. And because they are just a Fourier transform pair, they are completely equivalent ways to represent those. But then Gaussian processes also can be represented in sample space. So samples from a Gaussian process look something like this, and we can actually characterize these solutions in path space as well. And this path space representation, for example, this is the path space representation in terms of a stochastic differential equation for this process. So this is called Ornstein-Uhlenbeck process, which can be constructed as a solution to white noise driven differential equation. So the time differential of G is equal to minus lambda G plus the white noise. And well, by solving this by putting in white noises, we get these trajectories. But then we can also formally compute the mean of this. So these solutions, which is their zero mean, and then the covariance function, which looks like this. And so here we have the covariance function plotted. And then the spectral density, we can also solve that from the equation, and it looks like this, and it was the one which was depicted over there. And now there's an interesting property of this equation is that this is a Markovian process. So it's Markovian in the sense that so if we fix g at t, then there's like the past before t and the future after t. They are going to be independent. And this Markovian property is actually the key thing to for those Bayesian filter-based solutions for these GP regression problems. So let's assume that we have this type of Gaussian process regression problem. Then what this relationship quite quickly stated is that it turns out that this is equivalent to this kind of path space representation. So that well, we need to have the covariance function needs to be in a certain class so that there exists a finite dimensional stochastic differential equation of this kind of form. So this is a linear vector stochastic differential equation driven by white noise. And then the measurements are, so there's an additional matrix which kind of picks the right component from this vector. And then we have the measurement noise. But now this model, when we look at it carefully, so we can discretize it in closed form by using the theory of SDEs, I would say, stochastic differential equations. And now if we look at this model carefully, so this is indeed a linear state-space model, which is a special case of Bayesian filtering models or Bayesian filtering and smoothing models. And in particular, this is a Kalman filtering and smoothing model. So because it's a linear and Gaussian without any nonlinearities. So it means that we can actually solve this Gaussian process regression problem by running a Kalman filter and Kalman smoother on this model. And this is just like a straightforward conversion to different kinds of representation. So these matrices can be found by suitable computations starting from the covariance function. And so what it corresponds to is the Kalman filter is a forward recursion, and then a smoother is a backward recursion. So what happens is that we actually, like there's a Kalman filter going forward here. This is a continuous discrete Kalman filter, so it exists at every time step, like every continuous time. And then this is the filter. But then when we run the smoother, it produces this estimate. And this is exactly the Gaussian process regression solution. So this it's completely equivalent. We just computed that with the forward going thing and backward going thing. But the nice thing is that its time complexity is ON, not ON to the power 3. And also the like a time derivative of GP can be handled in this methodology, so that typically this state space representation contains the derivative as a component, or it can always be formed in that way. So then it turns out that over here we had, okay, so now it's, so like y was equal to some kind of matrix h times g. So we just need to replace that matrix with slightly different matrix to handle the derivative measurements. So actually the derivative measurement model was, it's the same except that we have a say c here. Just like what they look like if h was like this, so if the g vector contained g and the derivative as a component, so then h would be like this, and the corresponding c would be like this. So it's quite easy to form. So we can also handle derivative measurements. So how can we do then ODE solving? So we still use the same idea as with like a GP regression, is that we demand that, okay, so the derivative minus f evaluated that the value of the Gaussian process is equal to 0. So that this g as function of t kind of solves the ODE at the grid of values that we have. And in this state-based formulation, it tells that, okay, so C times G vector, which was the derivative evaluation, minus F at H times G, which was the evaluation of the GP itself, must be 0. Again, this is a constraint, and it can actually be handled as a constraint. But how this filtering formulation, so it's more convenient to actually rewrite as a pure filtering problem. So if we write that, if we define nonlinear function of vector Gn like this, so Hn of Gn is equal to C, G, and then F minus F, and this part, so it's basically this part, then we can define a measurement model. So Z is equal to H of G plus epsilon. And then, so this is a measurement model provided by that we interpret Z as a measurement. But now we can form our filter so that we always think that we observe that Z is equal to 0, which corresponds to, so that the constraint is satisfied, and then it's satisfied exactly when we say that this measurement noise variance is actually 0. But slightly more generally anyway, so we have the state space, discretized state-based representation for the dynamics, which corresponds to the GP prior, and then we have the measurement model like this. And now, if we look at this carefully, we notice that this is just a nonlinear filtering and smoothing problem. So we can use any of the available filters and smoothers to solve this problem, where now the G is the state, but anyway, it has a form of linear dynamics and a nonlinear measurement model. And that's indeed the principle in these solvers. So we can use any nonlinear Bayesian filter as an explicit probabilistic ODE solver. So explicit solvers are kind of forward going. So they don't use any information from the future. So indeed, for example, extended Kalman filter can be used to form such a solver, or sigma point filters or particle filters. So it's mentioned here. But then it's also possible to form iterated solver, which also uses the future information in a certain way. So iterated extended Kalman smoother is one very powerful method which actually computes a map estimate of the trajectory. So we can compute map solution to the probabilistic ODE problem by applying an iterated extended Kalman smoother on this resulting nonlinear problem. And it corresponds to some kind of global implicit probabilistic ODE solver for this problem. And so what the solutions look like. So this is a logistic ODE. And then indeed these solvers provide the mean solution and then error bars for the solution. So this is comparing two different approximations to the EKS solver. And yes, but then how to extend that to partial differential equations. So I'm only going to briefly discuss. So for example, if you have some kind of Cauchy type of PDE, so which is now functional of a spatial variable R as well. And then like a Cauchy type in the sense that we have an initial condition, then this can be seen as a very big ODE. So for example, we have been discussing Berger's equation, which is a special case of these. So this does that time derivative is equal to minus this here. So there's a, like over here, I have like quite the non-canonical notation. So maybe this notation with U is more canonical. So that's why I changed the notation. But this is a hard PDE with shocks in the solution, for example. But we can still handle it. So for example, one simple approach is to space discretize the PDE. This is also called method of lines, I guess. So you just discretize. I have an example in the next slide. For example, it's possible to use finite differences. That's one way. Another way is to use some kind of Galerkin, like a basic function expansions to discretize it, or then multiple other ways. But yes, so then the Gaussian process prior will not just be a temporal function, but it will be a space-time function of Gaussian process as well. But it turns out that that can be represented as an infinite dimensional SDE. And then that infinite dimensional SDE, which is, it can also be space discretized using the same method, for example. Okay, so I have examples like a finite difference method. So one way, then like with Galerkin, or then finite elements, which is a special case of those. But then this leads to finite dimensional state space models, which can be handled with EKF, UKF, and other filters and smoothers. Yeah, so this was the workers equation. So we can space discretize it like this. And after discretization, it's just an ODE. And then we can use the ODE solver. And then we can form some kind of infinite dimensional prior. So they look a bit more complicated, but in practice they are quite simple to handle. And then the EKS solver. So this is a simple example. So we can get both mean and then covariance. So the covariance measures the uncertainty in the solution. But of course, with other filters and smoothers, it would be possible to get better approximations. And the discretization is not very good either. But this is just an illustration. So conclusion. So this talk was about probabilistic ODE solvers, which aim to provide probabilistic uncertainty bounds for ODE solutions instead of worst case bounds as the classic ODE solvers do. And the basic idea is to replace the classical polynomial approximation with the Gaussian process, which provides error bounds. And these GP-based ODE solvers can be formulated or reformulated as Bayesian filtering and smoothing problems by using the state space representation of the Gaussian process. And then we can form implicit solvers by applying extended Kalman filters and related filters. And then, for example, iterated extended Kalman smoother provides an implicit global solution. And we can also extend the concept to PDEs. And here are some references. I guess this last one is actually maybe the main reference which I was basing this on. But the other ones are actually very much related. Yes, but